The James Webb Space Telescope, JWST, is not only an improvement over its predecessor, the Hubble Space Telescope, but it also features cutting-edge instruments designed to study the universe in unprecedented detail. One of its primary capabilities is its ability to observe in the infrared spectrum, which enables it to see through dense dust clouds and uncover phenomena that are hidden from traditional optical telescopes. This capability is crucial for studying the formation of stars and galaxies, as well as for detecting and characterizing exoplanets. Unlike Hubble, which primarily detects visible and ultraviolet light, Webb is equipped with advanced instruments such as the Near-Infrared Camera, NIR-CAM, the Near-Infrared Spectrograph, NIR-SPEC, and the Mid-Infrared Instrument, MIRI. These instruments cover a wide range of infrared frequencies, allowing researchers to investigate a diverse array of cosmic phenomena, from the earliest galaxies known to exist to the conditions of exoplanets. One of the most exciting possibilities offered by Webb is its ability to study exoplanets, or planets that orbit stars beyond our solar system. By observing these distant worlds in infrared light, Webb can analyze their atmospheres for signs of habitability. This includes detecting molecules such as water vapor, carbon dioxide, and methane, which are essential for supporting life as we know it. Webb's capabilities extend beyond simple detection. Its high sensitivity and resolution allow scientists to explore the chemical composition of exoplanetary atmospheres in detail, providing insights into their formation and evolution. Understanding the diversity of planetary systems in our universe and beyond is key to unraveling the mysteries of cosmic origins. Another major goal of the James Webb Space Telescope is to investigate the early universe by studying the first galaxies that formed after the Big Bang. Webb aims to shed light on how galaxies evolved from their initial formation to the present day. Its infrared capabilities are particularly well suited for observing these distant galaxies, whose light has been redshifted to longer wavelengths due to the expansion of the universe. Webb's deep field observations, akin to Hubble's famous ultra-deep field images, will capture pictures of some of the faintest and most distant galaxies ever observed. These observations will provide astronomers with valuable information about galaxy formation and the processes that led to their development over billions of years. In addition to studying galaxies, Webb will revolutionize our understanding of star formation and the development of planetary systems. Dense regions of gas and dust known as molecular clouds are the birthplaces of stars and planets. Webb's infrared vision allows it to peer through these dusty layers and observe the processes that result in the creation of new stars and planetary systems. Its ability to discern fine details in these star-forming regions will empower scientists to study the dynamics of gas and dust as they collapse to form stars. Webb will also explore protoplanetary disks, rotating clouds of gas and dust surrounding young stars where planets are born. By observing these disks in infrared light, Webb can detect the early signs of planet formation and provide insights into how planetary systems like our solar system came into existence. Understanding dark matter and dark energy is also crucial to Webb's scientific objectives. Dark matter is believed to constitute a significant portion of the universe's mass, yet it emits no light and interacts weakly with ordinary matter and radiation. Dark energy, on the other hand, is thought to drive the accelerated expansion of the universe. While Webb is not explicitly designed to directly detect dark matter or dark energy, its observations of distant galaxies and their distribution throughout the universe will provide critical insights into these elusive phenomena. By mapping the distribution of galaxies and studying their evolution over vast timescales, astronomers can infer the presence of dark matter and its gravitational effects on the large-scale structure of the universe. Similarly, Webb's observations of distant astronomical explosions and other cosmic phenomena will help inform models of dark energy and its impact on the universe's expansion. The development and launch of the James Webb Space Telescope has been a collaborative effort involving NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. ESA provided the Ariane 5 rocket for the launch and contributed key scientific instruments and expertise, while CSA supplied the Fine Guidance Sensor, FGS, which plays a vital role in stabilizing and directing the telescope during observations. International collaborations are essential for large-scale space missions like Webb, as they allow for the pooling of resources, expertise, and scientific objectives. Researchers around the world have eagerly anticipated Webb's launch, and are prepared to utilize its advanced capabilities for groundbreaking discoveries in space science and cosmology. Webb's role in education and public engagement also contributes to its scientific mission. The James Webb Space Telescope is expected to inspire the next generation of scientists, engineers, and astronomers. Its ambitious mission and cutting-edge technology captivate the imagination of people worldwide, showcasing the possibilities of space exploration and discovery. Educational outreach programs developed in collaboration with educational institutions and science centers aim to engage students and the public in the excitement of space exploration. These initiatives include curriculum materials, educational resources, and interactive activities that highlight Webb's scientific objectives and achievements, fostering interest in STEM, science, technology, engineering, and mathematics fields. Such outreach efforts contribute to building a scientifically literate society capable of addressing future challenges. Overall, the most remarkable images ever captured have been taken by the James Webb Space Telescope. Join us as we learn more about the James Webb Space Telescope and its potential to transform our understanding of the universe. The journey of the telescope began in 1996 when 3 groups of scientists and engineers from public and private sectors came together to explore the feasibility of building the telescope. In 1997, NASA agreed to fund additional assessments to further develop the technical and financial requirements. By 2002, the agency had selected teams to develop the telescope's essential components and formed an advisory group of scientists to assist with the design process. The telescope was named the James Webb Space Telescope that same year, honoring the former NASA administrator who made significant contributions to the Apollo program. When engineers and scientists began constructing the Webb telescope in 2004, they faced the challenge of devising new technologies and techniques to meet the mission's demanding scientific requirements. While space voyagers could repair and further develop Hubble from Earth, Webb would need to perform its tasks far from Earth, where assistance would not be feasible. Despite these challenges, the team successfully completed all 18 mirror segments and conducted extensive testing to ensure they met specifications. In 2017, the vision of the James Webb Space Telescope underwent extensive environmental testing in a massive thermal vacuum chamber to ensure its systems would function correctly in space. Finally, on December 25, 2021, at 7:20 a.m. Eastern Standard Time, the telescope was launched into orbit around the Earth. How it works. When people first hear about space telescopes, they might mistakenly think of them as just cameras. However, the James Webb Space Telescope, JWST, is far more sophisticated than that, which is why it took so long to move from concept to launch. Designed to observe celestial objects that are too faint or cold for conventional telescopes, the JWST can see phenomena like forming stars, galaxies, and planets. This powerful telescope is specifically built to capture infrared light, which is the primary way these distant celestial bodies emit heat. By focusing on infrared light, JWST can study objects obscured by gas and dust, providing clearer views of events happening far away in the universe. Additionally, infrared light allows scientists to analyze the composition and temperature of various objects on Earth. Infrared light plays a crucial role in various areas of physical science and technology. It helps researchers understand how stars, galaxies, and other large objects form and evolve over time. Infrared technology can also detect signs of chemical pollution in our environment. The JWST is equipped with a large array of mirrors, advanced imaging, spectroscopy instruments, and state-of-the-art thermal control systems, enabling it to operate effectively in the harsh conditions of space. Once launched and separated from its rocket, the telescope began its complex journey to its designated position, involving several critical stages, including crossing the Moon and unfolding various components. The telescope is now one of the most significant resources of its kind. Getting to space. Let's take a look at the crucial steps the telescope underwent to reach space. The launch was the first essential task. After launch, the solar array was deployed. On the 3rd day of its journey, 2 important components were unfurled, while astronauts were still aboard the rocket. These components were the major sunshields, which are essential for keeping the telescope cool and allowing it to function properly in space. The positioning of these sunshields was vital to ensure optimal performance during the mission. On the 4th day, the payload and instrument package were moved to their final positions. Although this process involved many intricate steps, everything went smoothly due to the telescope's design. The sun shield layers were then deployed, stabilizing the telescope. Following that, the film cover of the sun shield was opened, revealing a sun shield that is roughly the size of a tennis court. Once all components were in place, the sun shield and its parts were deployed. The 5 sections of the sun shield were then pulled apart. Over the next few days, the telescope underwent several more significant steps, including the installation of the secondary mirror and the structure to hold the smaller mirror in place on day 10. On day 13, the primary mirror wings were unfurled, giving the telescope its final shape. After completing these steps, the telescope was ready to begin its mission of observing distant stars and planets. The real purpose. What's fascinating about the James Webb Space Telescope is that it was not designed to accomplish just one task. It was built to address multiple scientific objectives. For instance, researchers like Daniel Eisenstein, an astrophysicist at the Harvard-Smithsonian Center for Astrophysics, can use JWST to look back in time and observe galaxies in their formative stages. This means that a planet that appears distant may actually be older than it seems. JWST can explore the early history of galaxies, helping to unravel how they formed and evolved over time. Its ability to see faraway galaxies allows scientists to gain a comprehensive understanding of galactic formation and development across various stages. The telescope excels in observing distant galaxies because it can detect infrared light, which is particularly useful since the universe is expanding. This expansion stretches the light from these distant galaxies to longer wavelengths, shifting it from visible or ultraviolet light to infrared. Because of its large size and cold operating temperature, JWST can look much deeper into space than other telescopes. This capability allows scientists to observe galaxies as they form and evolve, providing insight into the universe's evolution over time. Studying star formation. Scientists examine stars from the specific locations where they are born, namely from dense clouds of gas and dust known as nebulae. These clouds are so thick that visible light cannot penetrate them, making it challenging for researchers to study these areas with optical telescopes. In contrast, infrared light can pass through these dusty clouds more effectively than visible light, enabling scientists to observe the cores of star-forming regions in ways that were previously impossible. Due to its ability to detect infrared light, the JWST will allow researchers to study these regions in unprecedented detail. An infrared space expert at the University of Arizona, Maria, the lead researcher for one of the telescope's cameras, explains that this is possible because red light has a longer wavelength, allowing it to penetrate dust in our atmosphere more efficiently than blue light. Infrared light can also reach deeper into dusty areas than visible light, which is why the sun appears redder at night than during the day. Since JWST is adept at detecting infrared, it can explore star formation more effectively than the Hubble Space Telescope, which has only been able to study star formation superficially. With JWST's broader range of infrared wavelengths, scientists will gain deeper insights into how stars are born and evolve. The James Webb Space Telescope was built and assembled from 2012 to 2013. They are challenging to study because they can trap light, components being developed in various locations worldwide. Construction of Webb's sunshield layers began in 2013. These layers protect the telescope from excessive heat, allowing it to operate effectively in space. Over the next several years, Webb's various scientific instruments underwent rigorous testing, including exposure to high temperatures and vibrations. Simultaneously, the telescope's 18 individual mirrors were carefully mounted on its backplane. These components were assembled and tested at NASA's Johnson Space Center in Houston, some of the most complex objects in space. However, scientists can observe the effects of black holes on nearby stars and galaxies. Various telescopes, including X-ray telescopes, have been used to examine how the intense gravitational forces of black holes cause nearby stars to heat up and become active. With the launch of NASA's JWST, its infrared instruments will provide an enhanced understanding of black holes. Researchers will be able to learn more about the intricate physics occurring around black holes by observing the cooler gases and stars in their vicinity. Observing exoplanets. When studying stars in dense, dusty regions of space, it can be challenging to examine them using traditional telescopes. JWST is essential for overcoming these obstacles since it can capture light emitted by the stars themselves, even in the presence of dust clouds. This ability enables researchers to study areas of space that are otherwise obscured. The James Webb Space Telescope can detect and analyze light from stars and other celestial objects across a broad range of wavelengths. In summary, the James Webb Space Telescope represents a significant advancement in our ability to observe and understand the universe. With its advanced infrared capabilities, it promises to transform our comprehension of fundamental concepts such as the origins of the universe, exoplanetary systems, star formation, and the elusive nature of dark matter and dark energy. As the successor to the Hubble Space Telescope, JWST builds upon decades of scientific progress and technological innovations, paving the way for future discoveries in astronomy. By looking deeper into space and exploring frequencies beyond the reach of previous telescopes, JWST will uncover new insights into the mysteries of the universe, inspiring awe and wonder in people of all ages. As Webb embarks on its mission to explore the cosmos, both scientists and enthusiasts eagerly await the discoveries that lie beyond the stars.